Hi, welcome to this new video on support reactions. This particular video, we're going to see three problems, okay, in which we'll see how to determine the support reactions. Let's start with the first one. So in the first problem, we have two spans such as AB and BC. Okay, the span details are given here. Apart from that, we have these two supports such as a pin support at location B and then an inclined roller support at this point C, right? So the inclination details are mentioned here. If this is the angle theta, one can find that the cos theta value and sin theta value are as is mentioned here, right? So first step is to draw the free body diagram. When we draw the free body diagram, we need to represent the reactive components, right? So as is a pin support, we directly get VB and HB as we see here. How about this roller support? We know that at a roller support, we will have a single component of reaction such that it is perpendicular to this surface, right? So either it should be pointing upwards like this or it is pointing downwards like this. Which one will be the right one? So in order to understand that, what one can do is one can imagine removing this support and then see how this load is going to cause the rigid body rotation of this particular beam about this point B. Okay. So for time being, forget about this particular support at this C roller support. So after removing that, what is going to happen if this UDL is applied? The beam will have a tendency to move like this, right? To rotate about the point B. Right? So now in order to reinstate the beam in its original position, a reactive component like this should be applied, right? So and then from this we'll understand that this reactive component should be directed like this. Okay. So it can't be directed in this manner for equilibrium. So that is the logic with which this is directly shown downwards, right? So one can use this logic and directly every time determine which direction should be the reactive components be, right? And then what is the next step? Now we need to resolve this along the global XY axis, right? So if this angle is theta, one can see that this the inclination this reactive component makes with the vertical is also theta, from which one can show the resolved components are VC cos theta and then VC sin theta as we see here, right? So overall, what are the number of unknown reactions here? Only three, such as VB, HB, and VC. Now, in order to solve for them, we just require three equilibrium equations, right? So if we know them, if we use them, we can directly solve for the unknown reactive components, which means this is a statically determinate field, right? So that's what we are going to do next. First, we are starting with the moment equilibrium equation. We are going to write summation of moment about this point b equal to 0, right? You can do with any point actually. You can choose this point, or actually you can choose any point. So first we are going to solve for VC and then we are choosing this particular point B, right? So now what does this expression say? This expression says that the anti-clockwise moment or counterclockwise moment is equal to the clockwise moment, right? So the clockwise moment will be due to this VC cos theta, okay, into this span. So here we have this span is 20 meter into VC cos theta is equal to the counterclockwise moment due to the UDL, right? So due to the UDL, the counterclockwise moment will be equal to the load into the lever arm, right? The load is equal to 2 into 10, right? 2 into the span is 10 meter into it will be acting here at this midspan of this particular span, right? So that will be equal to 10 by 2, that is 5 meters, right? So overall we can write it as 2 into 10 square by 2, from which you can determine the value of VCS 5 into root 10 11 10. The next step is to use summation of original forces equal to 0, that is the original equilibrium. Here we have only these two original forces. Directly we can say therefore HB equal to VC sin theta. You know the value of VC already here, from which we can say that HB is equal to 15 kN. Once that is done, what needs to be determined further? We just need to determine what is the value of VB, right? The only remaining equilibrium equation that we have here is summation of vertical forces equal to 0. Just invoke that equation. It says that sum of upward force is equal to sum of downward force. The only upward force here what we have is VB, that is equated to sum of downward forces. Sum of downward forces are due to this UDL and then VC cos theta. Okay. So this UDL's contribution is given as 2 into 10. Here 10 is the span's length and then this is VC into cos theta. So once you use those values, you can see that VB equal to 25 kN. Right. That's all. We go to the next problem. Here we have a span CF, okay, which is lying on top of this span ABC. So now we will start with this one first, then we'll move on to the one which is lying underneath here. Why can't we do otherwise? Because if you directly start with this, the problem is you don't know what is the reactive component here. There will be three reactive components. Okay, so it is not uh, suggestible to start with this. Okay, so straight away we'll start with this one. We'll solve for these two reactive components. Once we know that, we can use that here, and then we'll solve for the reactive components which are there in the being ABC. Okay, so when we start with the span CEF, we need to first start with these two supports here. As there are roller supports, we'll get two reactive components such as BC and BF as we see here, right? So once we know them, once we mark them, the next step is to determine them using two equilibrium equations. As we have two unknowns, we can use two equilibrium equations such as sum of moments equal to 0 and then sum of vertical forces equal to 0. First, we are going to use this condition imposed on this particular point F. So 12 times VC equal to 960 times 3, right? So from which you get the value of VC, right? It says sum of counterclockwise moments equal to sum of clockwise moments. The next one is VC plus VF, sum of upward force is equal to downward force 960 kilonewton, from which we will get the value of VF as 720 kilonewton, right? So once this is done, what is the next step? We need to take care of this span ABC. So once you know the value of VC for this span CEF, you can use that for this span ABC, right? For equilibrium, if this particular reaction for span CF is upward, this force, there will be, I mean to say, there is going to be a pair of forces. That is, if this is upward, there will be a downward force which is acting as a reaction on this being ABC. Okay, that's what I'm showing here. So for this force, there is a pair. Okay, I mean the component VC which is acting downward on span ABC. Right. Therefore, as you know the value of VC, only two unknowns are here, such as VA and VDA. Right. So then you use the equilibrium equations again, that is sum of vertical force equal to 0 and then sum of moment over point D equal to 0. Okay, once you do that, you can solve for the value of VA and VD. This is straightforward, so I'm not going to explain. If you understood this, you can also carry out the same operation here, right? So just it says that sum of counterclockwise moments equal to sum of clockwise moments. So when you rearrange, you will get the value of VA. Here, this expression says the sum of upward forces, that is VA plus VD equal to 900 plus VC, from which you can solve for the value of VD, right? So that's it. This last problem we have a moment release here and then a shear release here. So is this beam statically determinate or not? It is statically determinate. Why? Because we have how many reactions here? 2 here plus 1 plus 1. Totally 4 reactions here. And how many equations we have to solve for them? 4. How? Summation of Fy equal to 0 as usual. Summation of Mg equal to 0. So there are two equations. We don't use summation of Fx equal to 0 as the beam is not acted upon by any horizontal force, right? So these two are there, and apart from that, we'll get two more equations due to the presence of these two releases, right? So here, because of the presence of this moment release, you will say the bending moment equal to 0 at this point. Okay, similarly, because of the presence of shear release here, we will say the shear force equal to 0 here. Okay, we'll use that in due course of time. We will start with the span CV first. Okay, then we will take this span EBC, then finally we will see what happens with A. So first span is CD, that is shown here. This is a roller support, and means we will show this component VD here, which is the reactive component. Now when we come to this particular joint C, this is a shear release, right? Therefore you can't see any shear force here. However, there should be a bending moment, right? So we're assuming it to be clockwise here, and then we are showing it as MC, right? Now we have two unknowns here, such as VD and MC. So you can use these two equilibrium equations, such as sum of vertical force equal to 0 and then sum of moments equal to 0. We are imposing the above point. Now, when we start with sum of vertical force equal to 0, this upward force should be equated by the downward force due to the UDF. So you can see that VD equal to 2 into 2, from which you will see the value of VD equal to 4 kN. And then we are going to use summation of moment over point equal to 0 to solve for this value of MC. Okay, this is straightforward. You can directly do it. This counterclockwise moment equal to, the clockwise moment equal to the counterclockwise moment, which gives the value of MC as 4 kN meter. So once this is done, next we are going to take this portion. Now this is a moment release, this is a shear release. Mind that. So as at C we have a shear release, we will have a bending moment, but this is a moment release, okay, which means no bending moment will be there. However, shear force will be there, right? So we are showing this as V, which is the shear force. What about this VB? That is a location where we have this roller support. Therefore, there will be a reactive component VB, right? We are assuming these two are acting upwards initially. Okay? And why this is counterclockwise here? Because when we solve for this portion, we already established that this is a clockwise moment, right? So here for equilibrium, there will be a pair of forces, right? Internal stress is left and the bending moment MC, right? As this is clockwise here, this should be counterclockwise here for equilibrium to be satisfied, right? And these are assumed directions upward. Now, how many unknowns do we have here? V and VB. Okay, and then again we can use these two equilibrium equations. That is sum of vertical force equal to 0 and then sum of one about a point equal to 0. We are starting with the point E here, okay, to solve for the value of VB, right? So when we take moment over this point, what is going to happen? This VB into 1, okay, plus MC. These are the summation of counterclockwise moment. Now that has to be created by the clockwise moment. The clockwise moment is going to be only due to trapezoidal load here, right? What one can usually do is one can decompose this trapezoidal load as a combination of rectangular and then triangular load. Accordingly, one can use the centroid details one knows about the triangular load and then this rectangular load. I am not doing that here. I am actually finding the moment due to the presence of trapezoidal load itself. Okay, how do we do that? One can do that by using this expression here, that is the span square divided by 6, okay, into 2 times this intensity 3, okay, plus 1 time this intensity 2. Okay. So if you use this formula, you can do it, you can find that expression and actually implement it here. Okay. So this gives you what is the moment generated due to the presence of this trapezoid load here. Okay. So once you simplify, you will get the value of VBS minus 8 by 3 kilonewton. What does this negative sign indicate here? It says that the assumed direction upward is not right. It is incorrect. So it is saying VB should be rather downward. Okay. You need to account for this when you include the value of VB in the remaining expression when you solve for other unknowns. Okay. The only unknown remains to be solved here is VE, that can be determined using the condition that sum of vertical force is equal to 0. That is, sum of upward force is equal to sum of downward force, right? Forces I mean. So VE plus VB should be equal to the force due to this trapezoidal load. Okay. So VE plus VB equal to 3 plus 2. Okay, that is, we are averaging out this here into the span. Okay, the span is 1 meter. And then mind that we need to use this value of VB as such with the negative sign itself here. Okay. So when this VB goes to the right hand side, it will become plus 8 by 3. So 5 by 2 plus 8 by 3. Okay, which gives a value of V equal to 31 by 6 kilonewton. This is positive, which means the assumed direction of V, that is upward, is fine, correct. Okay. So once we are done with this, the remaining span is just AE. Now we see that this V is upward, which means when we take this span AE at this end, this will be downward. Okay. So we are moving on to the remaining span AE, right? This span, okay, which contain the trapezoidal load like this, had the value of, the V acting upwards. Okay, so for equilibrium, this V here for the span, AE should be downwards, right? Apart from that, what else is there? We need to consider the condition that this joint A, support A is a fixed one. Therefore, we need to show the reactive component BA and then the reactive moment M, right? So we're assuming the directions like this initially here. And as we know the value of V, the only unknowns are MA and BA. So again, we can use a conditional summation of vertical force equal to 0 and summation of moment over point equal to 0. This is straightforward. One can do that. Just I will give you a brief explanation. So here, what are the forces acting upward? Only VA is acting upward, but we have two downward forces acting in. such as VE and then this uniformly varying load, right? So VE plus of base into the intensity should be equated to the upward force VE, from which we get the value of V as 43/6 km. And finally, to solve for the value of MA, we're going to take sum of moment about this point equal to 0, right? So here, the only moment which is counterclockwise is MA. Okay, that should be equated to the sum of clockwise moments. Clockwise moments are 2 times VE, right, plus the clockwise moment due to the uniformly varying load, right? So 2 times VE plus the load into lever arm, right? So half base into the intensity is the load into lever arm is 2 times 3 into 2, right? So this half base into 2 is directly mentioned here as 2. This lever arm distance is 2/3 of 2. That is, the centroid is located at a distance of 2/3 times this span 2, right? So which is 2/3 times 2. From which you will get the value of MS 13 kilometer, because you know already the value of, V is already determined from the previous span. That could be used here. From which you will get the value of MAS 30 Newton meter. Right, that's it. Hope this particular video helps. We have seen three different kinds of problems. The first one contained inclined support. The second one is the case wherein we had one beam resting on top of the other, and in the final one, we had a beam wherein we had two releases, such as moment release and then shear release. Right? Thank you so much for your passion listening. We'll meet.